curve sketching. So example 8 asks us only to find the max min values, and so I don't have to do a full curve sketch analysis here, but I will need to take my first derivative and find my critical numbers in order to do this question. So a couple of things to note. I'm working in radians on a restricted domain, okay? So I'm only looking at 0 to pi, okay? And I'm in radians, so my answers should be in radians, okay? So we're going to start with taking the first derivative in order to find our critical numbers. Okay, so what is the derivative of y equals 2 sine 2x plus 4 sine x? Sorry, plus 4, oh my goodness, plus sine of 4x. We're good there. Okay, so y prime is equal to 2 times the derivative of sine is cos of his argument 2x multiplied by the derivative of the argument, which would be 2. Don't forget your dinner. Plus the derivative of sine 4x is going to be cos of the argument 4x multiplied by the derivative of 4x, which is 4. So what does this look like? 2 times 2 is 4. So I have 4 cos 2x plus 4 cos of the argument 4x. Now those are different because the arguments are different. So now we're going to try and find our critical numbers out of this. So before I can find my critical numbers, I'm going to see if I can try and tidy this up a little bit to try and factor it, because right now in its given form, it's not looking like it's very easy to find those critical numbers. I can take out a 4. So I'm going to have cos 2x plus cos 4x. And because my arguments are different, I'm going to be looking on my identity sheet to see if I can get those arguments to match in order to actually find the critical numbers. Okay, so this is actually a double angle identity. So is the cos 2x. But let's work with cos 2x for a minute and see what we can do with this. So cos 2x on my identity sheet is equal to 2 cos x. I wanted to write, cos x on my identity sheet is equal to 2 cos squared x minus 1 on my identity sheet. So what happens when I'm looking at the 4x? Okay, so that's really 2 times 2x. Okay, this is really 2 times 2x. So that would be equivalent to 2 cos squared of the argument 2x minus 1. So this part right here, the x is the 2x, all right? So those two match, these two match, all right? So I'm going to now replace in my derivative here the cos 4x with this new piece here. So plus 2 cos squared multiplied by 2x minus 1. And then I am going to actually just get rid of that 4. I'm going to divide the 4 to the other side. 0 divided by 4 goes away. Get rid of that. Okay, so we now have that 0 is equal to, let's reorder this, sorry. Let's see, we have 2 cos squared of 2x plus cos 2x minus 1. All right, so now the question is can I factor that? Well, what if we said let x equal to cos, we shouldn't use the same variable. Let a, that would be better. Let a equal to cos 2x. Then I would have 2a squared plus a minus 1 is equal to 0. And that's a quadratic that we can factor. Excellent. So that factors to 2a minus 1, a plus 1. 2a minus 1, a plus 1. And I'll let you work out the factoring on your own if you don't believe me. And then when I go back over here, I can rewrite that as 2 cos 2x minus 1, that's the first factor, multiplied by cos 2x plus 1. And now I have my two factors, and now I can actually go ahead and try and find some critical numbers out of this. Okay, earlier on, it was pretty tricky to try and find those critical numbers. So now I'm looking to solve each of these factors to find critical numbers. So the first factor is 2 cos 2x minus 1 is equal to 0. So this will be cos 2x is equal to 1/2. And then the second factor was going to be that cos 2x plus 1 is equal to 0. So we would have cos 2x is equal to -1. Now back in 30, we would then use an identity again to substitute this in. So we'd go back to our identity. We say cos 2x is 2 cos squared x minus 1. We'd tidy that up and solve so that our argument was only a single x. I'm going to show you a way to solve this without having to do an identity. And if you don't like it, then go back to the Math 30 and substitute in your identity and go ahead and solve like you would have in 30. But if I look at this off of my unit circle, and I am looking to think about cos x is equal to 1/2 here for just a second. So cos x is equal to 1/2 at pi on 3, where the x coordinate is a positive 1/2, and also down in quadrant 4 at 5 pi on 3, where I have a positive 1/2. Okay, so right now I have a single x being equal to pi on 3 and 5 pi on 3. But my argument isn't a single x, my argument is 2x. So what has happened, if we think back to transformations, what's happened is I've actually had a horizontal stretch of a 1/2 happen to my graph. So if I actually apply that horizontal stretch of a 1/2 to these angles, I will get my single x to solve for this equation. I'll get the correct x that I'm looking for. Instead of the answer being pi on 3, I'm going to have pi on 6, and a stretch of 5 pi on 3 of a 1/2 would give me 5 pi on 6. And those actually fit my restricted domain, which was from 0 to pi. 5 pi on 3 was not actually in my restricted domain, but because I hadn't actually performed the horizontal stretch on it, it didn't matter at the point that the domain didn't quite fit. Okay, so critical numbers for the first case are pi on 6 and 5 pi on 6. And then in the second case, again, if I'm going to use this whole idea of a horizontal stretch happening, I'm going to look at where cos x is equal to -1 to start with. So that would be at pi. Okay, so I would be thinking x is equal to pi if I was just thinking it was cos x. But again, we have it being that it's an argument of 2x, and then I apply the horizontal stretch of a 1/2, which allows me to find the x that I need for this scenario. And then I get that the x is pi on 2 for our restricted domain of 0 to pi. And again, you could totally go through and say, I don't like that method. I want to go and use my identity that says cos 2x is 2 cos squared x minus 1 is equal to -1. And we would go ahead and solve this. We could have done this for the other factor as well. We would have gotten that 2 cos squared x is equal to 0. Cos squared x is equal to 0. When you divide the 2, so you take the square root, cos x is equal to 0. And you'll see that you actually end up at pi on 2 and 3 pi on 2, but that's outside our domain, that 3 pi on 2, and so we are getting that critical number of pi on 2. All right, Moving on. Now we're going to do our intervals of increase and decrease. And so we're looking at our number line, and we have a restricted from 0 to pi, and we had 3 critical numbers. We have pi on 6, pi on 2, and 5 pi on 6. And from here, I want to pick numbers that are in between here. And so if you don't like these radians, then there's nothing wrong with, I'm going to convert this all into degrees so I can find numbers in degrees. Just set your calculator to degree mode and go ahead and work with your degrees. Okay, so I find that to be a little easier. So I'm going to test 15 degrees. I'm going to test 45, 135, and 165. And I'm going to put that into my derivative. And you can just use the derivative in any of its form. I used y prime is equal to 4 cos 2x plus 4 cos 4x. That was the derivative that I used. And then I just plugged in 15 degrees for x, 45 degrees, etc. And I was in degree mode. And I found out that it went positive, negative, negative, positive. So I went increase, decrease, decrease, increase. And so I will see that I have 1 max happening and 1 min happening. All right, so from here, I am going to evaluate. Last thing is those max mins. Okay, so we're going to evaluate at our critical numbers and at our endpoints. So let's do the endpoints first. Okay, so if I evaluate f of 0, I'm going to get 2 sine 2 times 0 plus sine of 4 times 0. So sine of 0 is 0, so that just equals to 0. That was easy. And then the second one I'm going to look at is f of pi. So 2 sine 2 pi plus sine of 4 pi. So again, at 2 pi and 4 pi, the y value is 0. So this is equal to 0 as well. So I have the point pi and 0. And then I'm going to do my critical numbers. Okay, so at pi on 6, we were looking at that being a max. Okay, so I'm going to do f of pi on 6. So plug that in. 2 sine 2 times pi on 6 is going to give me pi on 3 plus sine of 4 pi on 6, which would be 2 pi on 3. Sine pi on 3 is equal to root 3 on 2. So this is 2 times root 3 on 2 plus sine of 2 pi on 3 is also root 3 on 2. So what do I have here? 2 plus 1, I have 3 root 3 on 2. So there's my max at pi on 6 and 3 root 3 on 2. That's definitely my max. That's bigger than any of those zeros that we got. And then the last one, hopefully before the video times out, would have been my min happening at 5 pi on 6. So plug that in. 2 sine 5 pi on 6 times 2 would give me 5 pi on 3 plus sine of 4 times that is 10 pi on 3. And 10 pi on 3 is also equal to 4 pi on 3. So sine of 5 pi on 3 is negative root 3 on 2. And 4 pi on 3 is also negative 3 on root 2. And so this is going to give me negative 3 root 3 on 2. So I have this absolute min happening at 5 pi on 6 and negative 3 root 3 on 2. And he's an absolute for the domain that we were given. And this one also is an absolute for the domain that we are given because we checked our endpoints. All right, So that's the end of max mins. We'll come back and look at the points of inflection question. Forgot that I gave myself extra paper there.